Okay, now it's recording. Good morning, everybody. I hope everything is okay and everybody's fine. I'd like to thank you, Vinicius Botechia, today for the seminar. We are gonna follow the steps as I gave in the first class. We have seen the red part, which is the model, the green part, which is the model construction in the first classes. Then Célio talk about the red part, which is the data simulation or history matching part. And today we're gonna start a set of seminars that are gonna talk about the production strategy, how to select the production strategy. Next week we're gonna see how to deal with uncertainties and so on. So thank you everybody for being here. Thank you Vinicius for the seminar. So I'll give the word to Vinicius. Thank you.
Thank you, Dennis. Good morning, everyone. Thank you for watching this presentation. First of all, let me introduce myself. As said, my name is Vinicius Botechia. I made my master, my PhD here with Professor Dennis, and I work in SIN since 2013. I've been working some projects, most of them related to production strategy. Now I'm coordinating the LIBA project. I think there are some students, at least Andrea is working, will work with in our project. And I'd like to thank also Ana Teresa that she gave this lecture in the last few years, and she collaborated to make this presentation, pass some reference, and so on. So let's start. First of all, starting with an introduction, when you talk about the selection of production strategy, we aim to find the best field performance. But of course, we're aiming this best performance according to something, right? So you want to define some objective and try to find the best way to do this objective, right? But in general, we try to do the highest recovery with the best possible economic efficiency. And there are several tools to do that, such as simulation, optimization methods, economic analysis, and all these tools can be combined and used to achieve these goals when we talk about the selection of production strategy. I forgot to tell in the beginning, I'll make the presentation in English because there are some people don't speak that don't speak Portuguese. If someone doesn't understand something, can ask in Portuguese, then I can answer in Portuguese. But I try to do my best to talk in English here. All right, this is a scheme from a general field life cycle, right? First of all, we have the exploration period. You start with the discovery. When you locate the field, where is the location of the field, then you have to evaluate and to estimate the amount of the reserves that you expect to have in your field. Then you have the production phase. This phase varies among some authors. They cause everything here of development, but in general, we have this phase that is regards development and production phase, right? First, the development. This is when you are deciding which are your facilities, when you design the facilities and you will install your facilities, right? This is the development phase. And then we start the production phase, which is when the production actually commences, right? So you have a fluid flow and have a data here from the production and so on until the end of the economic field life cycle, right? Which is the abandonment time. Here in the scene, we name a little bit different this production phase, and we name a management phase. But in some companies call management everything, right? Because you have to manage the field since the beginning, so they consider development also as management, but it's just a matter of nomenclature. And I'll talk a little bit more afterwards, but we say this phase as development as well, and this phase, instead of production, we say management phase, right? After the production facilities are already installed, but I'll talk with more details later. So the selection of a production strategy is a complex task and involves a multidisciplinary effort, since you have many people working for the same objective, right? So you have to join and integrate reservoir engineers, production engineers, geologists. Mainly nowadays, you have data processing specialists and economists, right? Since nowadays have many data to work, you have other people working with inside this team, right? Software developers and so on. So you have geologists who understand the reservoir, and engineers have the responsibilities to develop the development plan, right? The main role of the reservoir engineer is to forecast the behavior of the reservoir. Now talking about the phases of development, have here a simple scheme here about the field life cycle again. Have first a build-up phase that can happen or not. And sometimes a company can drill all the wells, and then the platform comes and it can connect all the wells at the same time the platform. But in general, what happens is this: we have a schedule of well opening, of well drilling, and we have a build-up phase that have this kind of form when wells are opening along the time, right? And then when the production of the wells reaches a plateau, you have the plateau phase. So the reservoir is producing at this time at the capacity limited by the facilities. And then we have the decline phase when the reservoir is no longer able to deliver fluids at this maximum capacity. And then here we have to do something to improve it if necessary, not to increase the production, to postpone the decline, some artificial lift, some pumps, or some other recovery methods, or some enhanced recovery methods, and so on. As I said, and the selection of recovery mechanism is a complex task, and since the beginning, it's important to make some decisions. And one of them, just to exemplify here, is the recovery methods, right? It's a big decision that it's important to take into account, depends on the case, of course. Since the beginning, have works here in our group that showed that if you choose the right recovery method since the beginning, you have the highest performance of the field, high recovery or highest economic performance. But of course, if you choose a method that is not the best one, you see that it was not the best one, then you can adjust by the control variables, and then I'll talk afterwards about that. So first of all, we have this old nomenclature: primary recovery, secondary, tertiary recovery. This old is not usual anymore, because this was kind of chronological, right? First of all, the primary recovery, where the field produces only with its natural energy. Then the secondary recovery was associated to water flooding after the primary recovery, but nowadays everything happens at the same time, and this nomenclature not used anymore, right? The tertiary recovery is nowadays called by enhanced oil recovery, and so on. So if it's possible, in some cases, you have to decide this thing since the beginning of the development plan. For instance, if you have a field that you know that produce a lot amount of gas, you can think about injecting gas or WAG since the beginning. If you have some viscous heavy oil to develop, you can use thermal mechanisms, or hypermobilities and the low temperature fields. You can use polymer and so on. So it's important to have in mind that if you can choose the method since the beginning, it's the best possibility. Here are some examples, some of the data you need to as input to the work. It's some reservoir data, such as oil in place, the air, the reservoir, pressure, permeability, porosity, fluids, and so on, right? Until another requirements like government regulations. Then this is how you this depends on the country and so on, the oil price, if you're doing pessimistic or optimistic estimates, and so on. Just to simplify here, just some of the input data is necessary to the engineers to work with production strategy. So, although we have softwares and computers to do part of the job, who is working with this are human people, right? So the teams will work in different ways. So we have a kind of subjective in this matter, in this issue. So two different reservoir teams will develop the same reservoir in two different complete ways, right? Because you have this human touch in the process and so on. So as I said, the selection production strategy is a complex task because it's related to decision in scenarios with high degree of uncertainties, right? You have to take many decisions when you know mostly nothing about the field, or depending on the stage of the field, you can get more information. But in general, you have to make high investments with many uncertainties, right? You have to decide, for instance, the platform capacity, the type, number, location of the wells, how you control the wells, the recovery mechanism, if you are going to use newer technologies or not. For instance, HISEP, that is a Petroleum technology. It's the gas liquid subsea separation. If we're going to use SUVs and so on, and how to take the best decision among these variables. So this is the role of the simulation, right? Summarizing the main role of simulation is to construct and operate a model whose behavior assumes the appearance of an actual reservoir behavior, according to Zahor. So the purpose of the simulation, the main purpose, is to estimate the future field performance under one or more producing schemes to assist the reservoir management, right? Nowadays, it's a practice very common in reservoir engineering, because reservoir engineering uses simulation as a tool. I listed here some items to discuss here. For instance, the simulation has lots of applicability. You can do simple tasks, just predict the performance, until you use it to very specific tasks, like to predict the performance of SUVs, to compare different technologies, to predict the performance of the life cycles, and so on. And it's relatively easy to use the simulators. They have lots of commercial simulators that have plenty of tools inside them, and there's not necessarily very sophisticated programming skills, right? So it's relatively easy to use it nowadays. The simulation is a tool that is flexible. You can update the information, you can update your model, you can make changes over the time, right, and make new forecasts. And the computational resource increase over time. So it's one more incentive to make true simulation to perform the selection of the production strategy, right? Nowadays you have jet fields, you have big models, and as you have bigger computers, parallel computing, more powerful clusters, so you can do this analysis in more complex cases. As I said, it has many uses, lots of applications, from simple forecasting to very specific tasks. You can also generate different production profiles under different exploitation conditions. It's important that the output of the simulator can be used as input to economics, right? Economic analysis, to generate cash flows, to calculate NPV, and so on. And the commercial simulators have provided with good well management routines that allow the engineer to specify the operation conditions in different hierarchical levels, like well group, reservoir, and field, right? So, as I said, the selection of production strategy is a multidisciplinary effort, And the simulation can be integrated with economic evaluation. As I said, the output of the simulation can be used as input for economic evaluation, right? In the companies, they do everything kind of separated, right? The reservoir engineers do their job, then go to the production engineers, then go to the economists to see it's viable. Here in our group, we try to do everything we can as integrated as possible. For instance, if you do the reservoir engineer point of view together with economics, we optimizing already using NPV, had some problems of convince them to use NPV, but I think that's the best way to integrate since the beginning, because you already take into account the costs and other things that is important to take into account in the development plan, right? So the simulation can be integrated with economic evaluation, with production engineering, right? So you can integrate with production facilities to see if you set the correct boundary conditions, to see if you set realistic conditions for the development plan, if it's possible to deliver what you expected, right? You can integrate with geoscience to have better models, to make better forecasts and take the best decisions as possible. So you can integrate geoscience with simulation, and you can have other tools like optimization algorithms and so on. So the final end of objective when you talk about production strategy is take decisions, and it can be in different stages of the field. It can be in the beginning, can be in the later stage of the field, but we are always talking about decisions. Yeah. So the simulators comes with, in general, well management routines, right? And you have, besides the defaults of the simulator, you have to set some things in the simulator, right? So you set well rates or pressures, implementing constraints or boundary conditions. You can implement operating policies by monitoring variables. I'll explain about monitoring variables later. Have to satisfy operate constraints at the different levels of hierarchy, right? To a group, reservoir, field, well, zones, and so on. Here, an example of task of well management routine. Well shutting using water culture area limits or minimum allowable oil rates, and so on, right? But I talk about this and I talk about the variables optimization. Here's some examples of production constraints. Some physical constraints are productivity, that is a function of reservoir work and fluid properties, saturation, etc. Or hydraulics, influenced by these factors, BHP, depth, and so on. You have the surface system facilities, choke size, flow line size. You have the surface facility capacity. These are constraints that are related to physical itself constraints, right? Because it's related to, for instance, to the radius of the well, how much the well can deliver of fluids, and so on, right? And have external production constraints, for instance, statutory controls, environmental regulations, political purposes, etc. Have operating guidelines to minimize some problems you can have in wells, such as corrosion and so on. You have the availability of the wells and of the platform of the facilities in general. You have the limit of the economic production, and sometimes your production can be not economic anymore. You have market constraints, right? Like in the some months ago, we have a crisis and problems in the demand of oil. No one wants to buy oil anymore, so it's a problem of market, right? I have another example here that's for fields that produce a lot amounts of gas. What you do with this gas? So these are some examples of some production constraints. Another thing I will talk a little bit here is that it's important sometimes to integrate production facilities, right? So instead of only simulating the reservoir perspective, you also simulate with the production facilities. Why to do that? First of all, to set realistic boundary conditions, right? And to see if the reservoir can deliver what you expect from the reservoir point of view. Not always necessary integrated production facilities all the time in all the optimization process. It is important first to check if it's necessary really to integrate, right? And for instance, in some cases, for instance, in Libra project, you have the bottleneck is the production it's the gas production, the high amount of the gas production. So the limitation is the gas production in the platform. So the production facility that was designed, it was able to deliver what you expected. But you had other cases, if you have oil cases, for instance, that made all the studies and then you saw that it is not possible to deliver what was expecting. It was necessary a pump and something like that. So just to take our attention regarding this issue, but João will talk with details in some lecture, I guess, next 2 weeks. So we'll talk better about this, but just to be aware that this exists and it's important to take into account sometimes. So they're starting talking here about the representation in the simulator. Have the hierarchy you have to follow in the management routines, right? Generally, it follows this structure, right? In different levels of the routine, right? Field, reservoir groups, you can change this if you like, if it is necessary. As I showed, you set the levels, you set the operating conditions, the constraints, and his pressures in order to do your simulations. So one simple example here about this field hierarchy and the representations of the simulator have this level 1, the whole field, level 2, 3 groups, namely GR1, GR2, and GR3, can be, for instance, in 3 different platforms for the same field. You have a level 3 if these 2 groups that are attached to are linked to group 1, and then the wells regarding all these groups. Just an example here. And in the simulator, we put as this, right? Group GR1 is attached to field to say that this group is linked to this another level, and the group 2 is linked to this other level, and so on. And we'll see my details soon. So I talk about how you declare these kind of things in the simulation file, right? We are talking about CMG simulators. Because it's what we have more alliances in the group, so we work more with the CMG simulators. So in the last section of the data file, we declare that the well in the recurrent data section, we declare the wells, groups, dates, and events. An example here, how to declare the producers. For some people who already work with simulation, it would be kind of boring this part, but who never saw simulation before, maybe it's part to have an idea how to do that. And well, first of all, we start declaring the producer, and optionally you can link to a group, right? So we declare the well name, for instance, well WL1 attached to group 4, and then we declare that is a producer, and then we set the operational constraints. Here, for instance, you are saying that the well will work is only until a minimum BHP of 50,000 kilopascals, and is operating at a maximum liquid rate of 8,000 cubic meters per day. And these are operating constraints, and these are monitoring conditions, right? So I will take actions here when some of these things happen. For instance, when my water cut reaches a maximum value of 0.95, the well should change. The same for GOR, when it's missing a max here, monitor max GOR 1016. When this happens, when the GOR of this well reaches 1600 cubic meters per cubic meters, then the oil should change. And the same for the minimum oil rate, right? And this is monitoring conditions to take some actions, right? And this above here are operating conditions. So when the well reaches this level of pH to B, it will be restricted by this level. It not produce more than this level allows, right? The same as for the liquid rate. And similar, you do the same for injectors, right? You declare the name of the wells and the initial group, then declare that the injector, you declare the fluid that is being injecting, you declare the operation constraints as in the producer case. So you set, for instance, a maximum BHP of 70,000 kilopascals, and the injector will operate only until this level. If you reach this level, it will be restricted in this amount. Same for the water injection. You also, in this section, define the oil geometry with this keyword geometry, right? So let's take a look into these keywords. And this keyword specifies that the oil bore is parallel to A, I, J, or K grid axis, right? In this case, a vertical well, so the right letter here is K, but it can be I or J for horizontal wells. I if the well is in this direction, and J if in this direction, right? So if you are looking above the reservoir from aerial perspective, then this is the radius of the well. This is a thing called geometric factor and depends on the position of the well inside the grid block. And this one also is another geometric factor, right? It's W-frac. It specifies the fraction of a circle that the well models. These two values in general doesn't change, right? I will show some examples of how to work with this, but in general, we use this one the way it is. You don't have to worry too much about this kind of standard to use. And this is the skin factor. Some examples of these two parameters, L-frac and W-frac. As I said, the values depend on the position of the well. If it's near the boundary of the reservoir, we avoid to do that, to put the well in the boundary of the reservoir, because you can change the grid, and when the grid changes from model to model, and you transfer the well from the grids, you can have some problems. The well can be outside of the grid, and you avoid to do that. And this I never saw happen. I never saw this. Then in general, you use this, right? This never changed. And that also don't need to worry. It's just to say that exists this. You should be aware. This is from some user guides, user's guide. So if you need to work with this, you can check that. And finally, you have to inform the perforations of the wells, so the completions of the wells, right? You do that with this keyword perf. So here we are talking about perf, and this keyword specifies that the well productivity will be calculated inside by the simulator, right? You can also use WE instead of GLA here, and you put directly the well index here in this column. But the most common thing to do is to use here this keyword and use and let the simulator calculate the well index. All right, and instead of that, it goes the factor form. I talk about this soon. But first of all, you need to declare the position of the well, right? So the first column in the I direction, the second column the J direction, the third column the K direction, right? The vertical direction. So in this example, we have a vertical well that was defined by the letter K here, that have 4 layers, and is completed in this block, in the IJ, and in these layers, right? In the vertical section. Here is the factor form. It's a multiplier for the well productivity. If it's 1 here, so nothing happens, but you can change here to consider uncertain, for instance, in the well productivity, right? So it's a multiplier for that. The stats, if the layer is open or closed, and here is a characteristic of the CMG simulators regarding the direction of the flow. In general, this doesn't change too much as well, so we don't have to concern about. And just a little observation here, you can have another keywords. For instance, in this PO bar, it's optional. It's kind of to use with a first step of integration of production facilities is used to calculate the pressure loss using the P-tube. Is the another CMG feature that calculates the pressure loss, makes integration production facilities, right? So this use you when are going to calculate the pressure loss, and you have already generated the tables with P-tube. I guess João will talk about that a little bit in 2 weeks. So here you're just saying that you're going to calculate the pressure loss for these wells using table 1. This number relates to the number of the table, and this is the depth of the well. We're informing here the depth of the well. And with this, you have to associate these new constraints, the minimum WHP, which is the pressure in the wellhead. Just to be aware, but it's not often used in a group, just if you're going to work with integrated with the production facilities. Another observation is a difference in the declaration of the wells regarding the IMAX and the GEN. IMAX is the black oil simulator, and GEN is the compositional simulator. It's similar, but you have in GEN you have one more option. Yeah, besides producer and injector, have also cycloprod. That is, you're informing that these wells, these producers, informed by this keyword, will be working for gas rejection, right? And if you use this, you also use this in the injectors. These are producers, and this is the fluid you are declaring the injectors. So you're declaring this in the injectors that you are injecting gas from the cycloprods wells, right? So just some people, if you work with GEM, and if you work with gas injection, we'll see this, right? The producers are not declared as producers, are declared as cycloprod, and then in the injectors, the fluid is cycling, it's not a fluid itself, it's the fluid that comes from the producers, the cycloprods. But who's working with IMAX don't need to concern about that. And finally, the declaration of groups, the declaration of constraints for groups. For instance, here you have this word gcomp. The gcomp sets some operating conditions for groups. In this example here, you have maximum production for oil of 30,000 cubic meters per day, and maximum water production of 2,000 cubic meters per day, right? And you have gcon is the keyword for injection restrictions. Yeah, you are setting for group 1 that our maximum water injection is 30,000, 35,000 cubic meters per day. And also you can declare events in the section of that file. The most common is to open and shut in wells, right? But you can have triggers, more sophisticated things to work with CV, to work with frag cycles. You can change the rates or the BHP's conditions during the life cycle and so on. But just to have an example here, I showed just how to open and shut in wells. First of all, you declare dates, and after this date, you declare the event that happens. For instance, here, you are opening these 2 wells in this date, right? And here you are closing this well in this date. Another possibility is to work with timing instead of dates, right? Timing substitute for date and specifies the number of days after the beginning of the simulation. For instance, here you have 1 year after the beginning of the simulation, the opening of these 2 wells, and in this day you having the closure of this well. I'm not sure if we can use the first days if you can use time. I think you need to declare first a date and then you go through times. I don't remember now because I don't like too much to use time. I prefer to use just dates. I think it's easier to work with, but it's another possibility. But people of that data simulation use more times than dates, So to generate history, they use this more often choose time. So there's these two possibilities. Another thing, you can emulate system availability with the keywords on time that specifies the fraction of time during which a well or group operates. What that means, for instance, for this time and on, or 1 year after the beginning of the simulation, I will apply on time for this well. Apply on time of 0.96. This means that the rate of this well will be multiplied by this factor. It's just like I say, during the long, if I think about the long term, in a long-term project, this well will not work 100% of the time. This well will work only 96% of the time, because there will be stops for maintenance, some problems of the well that you need to be shut down and then opens again. So you can do that putting shut-ins and opens of the well, but it's more common for the simulation models to do with the on time that specifies that the availability of the well, how percentage of the time the well will operate in the long term, in the average, in the average of the time. People who's working with short term or closed loop operations need to be careful with that, and to that in other ways, putting shut-ins as well. But for long term, this is a good way to do. So a simple example of this section of the data file. This well and recurrent data section starts with this keyword run. So after run comes everything I said since now. This is an example of a simple data file, right? You declare groups, link to other groups or not, then declare URLs, and you link to groups or not, and so on. So you declare the conditions for the groups, and you declare everything you need in your simulation file. It's important to put the shut-in after you declare your well, because if you not put it, the well will start producing when you declare it automatically, right? Even if you don't put open, here, if you don't close the well, it will start producing. So be careful with that. If you want to declare all the wells, for instance, the same dates, and then start opening, if you don't put shut-in, all the wells will be open in the same date. Here, talking fast about some classic strategies. This is direct line drive, which means align for instance, a line of injectors, a line of producers, another line of injectors, another line of producers. Have this another picture here. When you change A or D, you have what was called staggered line drive. It says in Portuguese, this is the best translation I got, injeção em linhas constas. When you change this A or D, you change a little bit this scheme, but it's kind of very similar. Have the classic 5-spot pattern, right? So when you have 5 points here, you have the injector inside a square surrounded by you have a producer inside a square surrounded by 4 injectors, and you have the inverted 5 spots here when you have sorry, this picture is wrong. This is the 7 spots. I made some mistake here. But the inverted 5 spot would be the opposite here, right? Would be 5 points, but the injector inside and the producers surrounding, right? And I'm sorry that these pictures are in Portuguese. I forgot to translate as well. So I have here 7 spots, the 7 spots pattern, where you have 7 points. The producer inside 6 injectors, and here the same thing, but the injector being surrounded by the producers. I guess there's something wrong with this picture. These wells are wrong. Just need to be just the corners here, and I think it's wrong in the book. I'm paying attention to this only now. Similarly, you have the 9 spots pattern. It's the same thing, but 90 points here, injectors surrounded by 80 producers. And here we have the inverted case, that is the producer is surrounded by the injectors, and here the injectors surrounded by the producers. I have another kind of schemes. For instance, have the peripheral injection, where you put the producers in the middle of the reservoir and surrounded by the injectors. This is common in fields to have this structure here, like I don't know how to say this, but like mountains, like little mountains. When the field goes like that, and you have the aquifer surrounding the field, for instance. People used to do this, injecting in the periphery of the reservoir and producing the middle. You have some Persat fields, and when they have some patterns like this, and we have also injection to the top. And when you inject the layers at the top of the reservoir and producing the lower layers of the reservoir, this is more common for reservoirs with gas cap, right? Because you can use the difference in fluid densities to make the injection production pattern. And similarly, we have injection to the bottom, right? Where you inject in the bottom, in the lower layers, and produce in the top layers. Usually do that when you have aquifer, when you have a well-defined water-oil contact. So you inject in the bottle and produce in the top. And both of these patterns can be used together, right? This first one is more from an aerial perspective, right? And this two is more from a vertical perspective, let's say. And type of wells, there are no wells. This we have horizontal wells of this type, multilateral wells, vertical, and directional wells is common for everyone. So after saying that, you have to talk about the whole issue, the main task of the engineers and the simulation, that is forecasting future performance of the field, right? And with this, that you're going to take decisions. So how we can predict the future performance forecast, how we can work with this data, how to use that, and I will focus more. You can do that with infinite possibilities, right? You can do that in lots of different ways. So I try to show some possible ways to work and to use the future performance forecast, right? This is an example of workflow, or how to use data. It's I took from a book. First of all, you plan the prediction case to run. You select different cases to be compared. You determine the input data requirements, and you have to be cautious with the transition from history to forecast, because you can have some problems in this transition. In our group, people studying this. You check data and the results, then you evaluate the predicted performance. These are some general, very general steps to follow, but I'll show another form in details. So as I said, you can visualize the future performance of the well or of the field under different predicting strategies. Another important role of the simulation task, that you can compare different operating strategies and take the best decisions among these different options, right? Examining a variety of scenarios and selecting strategy that will likely result in the most desired performance. But the most desired performance in regarding with some objective, right? Depending on what you want. You want more profitability, you want more recovery, you want to speed up recovery. Then have to define an objective and selecting a strategy according to this objective that you have. If you want to lower costs and so on. So to forecast future performance, you have to analyze some data, right? I put this in orange, the outputs, the simulation outputs that can be used for analysis. The most common to be used for analysis, but you can have lots of more information to be used, right? So the most common use the oil, water, and gas production estimates, rates and cumulative, water, gas injection estimates, rates and cumulative. You can use average reservoir pressure. You can use well bottom pressure, saturation pressure maps, and with this, you can use to generate cash flow and can use economic indicators together with this to make the forecast. As I say, in some companies, they make separate, the reservoir engineers deliver the things to the economists, then the economists see if it's viable or not. Here we try to do together, right? The optimization and so on. We already include the economic indicators, so you can have more sensitivity to the problem. You already take into account many issues like the costs. For instance, if you're doing polymer fluiding, you have to take into account the cost, right? Because the polymer will cover more oil, but it's worth to spend more money in this extra oil. Depends if this extra oil will be paid, right? If your extra investment will be paid, and I talk a little bit more about that. So how to use simulation? Basically, you can use if it is two ways, right? Deterministic when you use only one single simulation model, or probabilistic when you use multiple simulation models. This can be used when you have few uncertainties, and this is used more when you have uncertainty or risk analysis. But not necessarily these are made separate, right? You depends on the work flow, as I show in the closed loop process. Some steps of your probabilistic approach can be made using deterministic approach, right? It's quite confusing, but I will show some examples later. But you have to say what you need to know is that you have these two possibilities. Working only with deterministic case is not good because you have to rely a lot in your simulation model, and that's hard to happen because in the simulation model you try to emulate an actual reservoir, but it's very hard to get there very precisely, right? So you have to run a very refined model with a very refined grid, and so on. So it's to work only with deterministic is being avoided, but is being used to just some specific case, or if used together in some steps of probabilistic approach. Some example of an analysis of a deterministic case. You have here the gas rate. This is the case that I said that the bottleneck of the platform is the gas production. So what's happening here is the platform is limited by the amount of gas production. We have here the oil production, and here the oil production. And as I said before, the phases of the field life cycle, right? You have here here I have first an extended test, teste de longa duração, né? With 1 year of duration, and then you have the build-up phase that I showed. This is not good to see here, but when I show a picture of only this history part here, it's better to see the kind of ladder here, or the steps when the wells are open, then the plateau phase here, and the decline phase here. And an example here, when you're going to probabilistic approaches, you have many dozens or hundreds of simulation models, and have data for all of them, and have to work with all them. And I show something you can do with many simulation models, and have uncertainties. And not focus too much in uncertainties and in risk analysis, because you have a lecture specific about that, but I need to talk a little bit about that. So how work with probabilistic scenarios? Very summarized here, very basically. If you have, for instance, information such as seismic data or well profiles, use this information to construct the geological model. After the construction of the geological model, you make upscaling, you generate geostatistical realizations, you combine of known uncertainties, and then you generate the simulation models, multiple simulation models, right? And I'll come back to this later. But just to have a simple idea how is the workflow. Have data, which data to generate the geological model. You put the uncertainties, that you are think that you have regarding this information you have, or from analogous fields and etc. You combine them and generate, do upscaling and generating multiple simulation models. From risk analysis, I will talk about these things in some parts of the presentation. So I will introduce here the concept of the risk curve, right? The risk curve is not more than a graph that relates an indicator in the x-axis and the cumulative probability in the y-axis. Right, it can be any indicator you want. Here is the NPV, but it can be for NP, to estimate reserves, and so on. So we have here two examples. It can be, for instance, two different production strategies, one represented by the blue curve, and the other one represented by the red curve. And in general, people divide these in percentages. You can have infinite percentages here, but the most important ones most often used is this three: P90, P50, and P10. What they mean? They mean, for instance, P90, that is a probability of 90% that you reach values equal or higher than this value here, right? This is associated with proven reserves, right? Because it's very likely that you have this or more than this, right? P50, you have 50% of probability that you have values equal or higher than this one, right? So it's in general associated to probable estimates. And also we have the P10, is the probability of 10% to have values equal or higher than 10. So it's related to possible reserves in reserve estimations, and it's related to probabilistic, to optimistic scenarios, right? So in this part, you have even negative values for NPV, for instance. Here, have the pessimistic part of the curve. If everything goes wrong, you have this estimate, and you have the optimistic part of the curve, and have the most likely probable part here. And this is important in the risk curve, is to compare different project options to see if it's risky or not, right? And so on. So as I said, you can use this kind of approach or other ones to make reserves estimation, right? So the proven reserves is the quantity of petroleum that after the analysis can be estimated with reasonable certainty to be commercially recoverable, right? Under current economic conditions. The probable reserves are unproved reserves, which analysis suggests that are more likely than not to be recoverable. And the possible reserves are the improved reserves, which analysis of the data suggests that are less likely to be recoverable than the probable reserves. And let's see some example how to do that. As I showed, this is an example of a risk curve, and have the 3%. You have here the proven plus probable, and the proven plus probable plus possible, right? Yeah, you generally don't say like that. You just say proven, probable, and possible reserves. This is an example from the book that I took from Hero to Watt of the estimated reserve. So we have the distribution function of all these parameters, right? And from this, they calculate the reserves. In the book, they show these examples, as I said, in the percentiles, P90, P50, and P10. And this is the estimation from a probabilistic perspective, but you can go through for the that proposed for a deterministic perspective. They shows this example in that book as well. You have your reservoir here, but you have many uncertainties in the first place. You don't know exactly where there is oil and where there is not. So you drill a well, and you know only this is the proved, only where the well is, you are the proved reserves. As far you go from the well, is going less likely to have oil, right? Of course, close to the well, you have more probability to have oil, and far from the well, have less probability to have oil. So in this case, for instance, I have proved oil here, probably surrounding the well, and possible far from the well. So you are going to perforate another wells to delimitate in the area of the reservoir and to see where the well is, the oil is, and so on. So perforate another well here. You already discovered a discontinuity here, a non-reservoir region here. You have already proven all this region here and here, but this area here remains uncertain, right? It is in the initial appraisal stage. So the engineer proposed delineate a third well here, for instance. Then you can discover another thing such a new water oil context and a new gas cap here, and so on. And this is remake until you can delimitate your reservoir, and you can estimate where areas are proved, probable, and possible reserves from a deterministic point of view. Now we'll talk about some economic concepts that we will use afterwards. I'm going to talk about optimization and these things, right? I talked a little bit about NPV, but let's see in details what is it. This is a typical ENP cash flow. This picture is also in Portuguese because I took from this reference. I didn't translate, but you have two main phases here, three main phases, right? The exploration time that goes from local studies until the discovery and evaluation and development plan. You have here the approval of the development plan, and then you go to that phase that is development and production, right? So you have here basically first in our capex. The capex is the capital expenditures that are the investments, are the expenses the beginning of the project, like the investments in wells, in the facilities, the platform, and so on. So here in the production phase starts, you have revenues coming, right? So the cash flow becomes positive. Until here is only negative. You have only expenses, but from this point and on, you have production, you have revenues, and until here you call develop from here to here. You call development phase from here to here. People used to call production phase. We see here in the management phase, right? So we have revenues, and you take off the OPEX, the tax, and you have your profit, right? What is the OPEX? OPEX are the operational costs that occur during the life of the project and can be variable or fixed. Fixed are like the man hours, their expense do not change regarding the production. Now, the variable costs will change regarding the production. For instance, the costs for treating the oil, treating the gas and water, and so on, until you reach the economic limits for field, for producing the field. There becomes a time that the field is not economically viable anymore because higher water cuts, or higher GOR, and so on. So this is the abandonment date. Right? These are simplified components of cash flow. These will change according to regulations, according to the tax fiscal system of the countries, and so on. You can consider another things here, but this is for a simplified way to show a cash flow. We use the Brazilian tax system, right? Have here the revenues and discount royalties, government fees, uh, operational costs, abandonment costs, other government taxes, investments, and so on. The other possible things you can put in your cash flow are depreciation, special participation, under fees, and etc. And if you go to production share regime, is a little bit different because you have to discount the cost of oil, and is a little bit different. You have to take account the well productivity and so on. But you'll see the fiscal regimes later. So the most common economic indicator that we use in production strategy selection is the net present value. That is nothing more than the sum of the cash flows, but bringing to the present date, right, through a discount rate. That is this. These are here. So it's the sum of cash flows. Is the value of the time bring to the present, right? Are you calculating all my financial return and bring it to my present time, not necessarily today, but with the date that I choose, right? Basically, you can say that is the profit of the. It's not exactly the profit, but you can say that it's the expected profit of the project. Uh, for saying that, right? It's not exactly, but you can kind of say that. Uh, and this is used mainly when you're in deterministic or nominal cases, right? So when you're considering uncertainties, you have to use the other indicator. We use EMV, which is named the expected monetary value. That is the sum of them. Is the weighted average NPV, right? You weight regarding the probability of occurring of your uncertain scenarios. You weight your NPVs regarding that, right? So it's a weighted average of the NPVs, the EMV. So in many cases, just the return of the project calculated by the EMV is not enough to take a decision, right? Because you can have your higher returns, but you can also have riskier strategies with that. So it's necessary an indicator to quantify the risk of the project. And although the quantification, there is a degree of subjectivity in the decisions consider risk, because who is making the decision is a person, a human being, that can be more averse or more prone to the risk, right? And different managers, different decision makers, you take different decisions for the same case, right? So even if you quantify the risk, the final decision is you have a degree of subjectivity to what is to decide what's better to my field, right? Some people, what is riskier for me maybe it's not risky for you, and so on. That will depend on the profile of the profile of the decision maker. So I have some classical risk indicators here. For instance, mean deviation, the variance, standard deviation, that are statistical indicators. Everyone knows about these indicators, but these classical measurements, mainly the standard deviation is the most common. These are cash flow metrics, not only in petroleum fields, but in the stock markets, in the economics. They were already questioned because it measures the variability, right? Not measures the risk itself. It measures more the variability of the output, of the possible outputs. And the problem with this metric is that penalizes loss and gains at the same time. And this kind of counterintuitive, because we think about risk in chances of loss, right? You don't think about risk in the possibility of gain some gain that I was not expecting initially, right? So it's not good to penalize at the same time losses and gains. So another indicator that comes from Markowitz from a long time ago, and Susanna started using in our group, is the same deviation or the same variance, the same deviation, the root square of the same variance. The difference among the same deviation and the standard deviation is that the same deviation is related to the result being lower than a reference value, represented by this letter B here. So the calculation is similar to standard deviation, but is related to a reference value. For instance, you have a reference value in this black bar here. We consider the risk in this risk curve, in this example, this part of the curve. You don't penalize this part. This is the possibility of gains. So you don't want to penalize that. You're considering risk in this part. So if you compare different risk curves, all these parts of the curves will be considered out of risk, free of risk, and this part be considered in the risk calculation. Right? In how to choose the value of a bill, that will depend, right? Can be the highest EMV I achieved. In general, use that, but it can be 0. You don't want negative values, but everything that have the possibility to be profitable, you consider. Then there's several possibilities here. But I think Susanna will talk lots more about that. Explain more. In this example as well, you again, if these risk curves have two project options. For instance, the blue curve presents a strategy, and the red curve presents another strategy. So we want to analyze, for instance, which one is riskier, right? When you take a look at first, you say, yeah, the red curve is riskier, but it's not riskier itself. It's just looking at because it has only the more variability, right? Because you can have more gains with the red curve. If the red curve, you can reach these values of NPV. Instead of blue curve that goes only until here, but at the same time you can have losses higher than the blue curve in the red curve. So it's kind of difficult to say which curve is riskier among these two if you consider only the variability, right? But if you consider only this part of the graph, it's easier to see which one is riskier, right? The red curve is riskier because for the same percentages here, for the same probabilities, you have lower values of NPV for the red curve. So we always the red curve is almost always below the blue curve in this part, except for these little parts here. So if this happens, it's better to have the red curve, right? But if this happens, it's better to have the blue curve. So in this analysis, you can say that the red curve is easier if you use the same deviation, right? This is the reference value for same deviation, forgot to say, and so on. And Susan developed an indicator that's a multi-objective indicator that combines both parts of the curves, right? So you have uncertainty, you have to penalize the downside risk, and you can also weight the upside potential, that this part here we call upside potential, that the potential of gains that our strategy or our project option can achieve, right? And she'll talk better among this, but just to know that this exists. So you have indicator, you also already have indicator that combine both both parts of the curves, our probability of risk, our probability of losses, and our potential of gains. But Suzanne will talk more about that. Still regarding the risk analysis process, I talk a little bit about this, not enter into details, but one way to choose a strategy to consider risk is plotting a graph risk return, where is the risk measurements, this is the return measurements. It can be, for instance, EMV and some deviation here. And this comes from the portfolio theory from Markowitz as well, all right? Have been used for a long time, and it has already been criticized as well, but anyway. You have here, these blue points are project options, and you have here the efficient frontier. Which is the efficient frontier? This is the important thing here. The points inside the efficient frontier is the project options that I would choose regarding some level of risk. For instance, each project inside this curve has the maximum return associated to a certain level of risk. So, for instance, let's see these 2 points here. If your doubts are among this, is between these 2 points, these 2 options, of course you choose this, right? Because they have the same return, but a lower level of risk. So this option will discard, will not be chosen. This one can be chosen, but will depend on the profile of the decision maker, right? If a decision maker prone to the risk, he can choose that, but he can also choose this one, because to this level of risk, this is the maximum return that I can achieve. For this level of risk, this is the maximum return I can achieve. This picture is not very good, but suppose that the black curve here is above is crossing these points here, right? This black curve should be crossing these points here. So that is the options that I need to make regarding risk and regarding a return and the acceptance of risk. And I'll not talk about the utility, but the points here have the same preferences and so on. So I'll talk about this, I think. Anyway. So I think you can make a break of 15 minutes. I guess it's the half of presentation, and come back in 9:30. What do you think?